Somewhere in a muddy riverbed, there's a mineral sitting quietly in the silt that will one day help hold up a building half a mile tall. That sounds impossible. Rock found in river mud, the same stuff you'd scrape off your boots after a walk by the water, ending up inside the tallest structures humans have ever built. But it's true. And the paradox gets stranger the closer you look, because this mineral isn't rare, isn't glamorous, and isn't even particularly hard. It's soft enough to scratch with your fingernail in some forms. So how does something this humble end up load-bearing inside skyscrapers that scrape the stratosphere? The answer is zircon. And before you picture a gemstone, stop. This isn't about jewelry. Zircon is a dense, crystalline mineral that forms in ancient rock and gets weathered out over millions of years, washed downstream, and deposited in river sediment and coastal sands. It survives that journey because it's incredibly stable, chemically and physically, which is exactly why engineers care about it. But raw zircon in the mud isn't useful yet. It has to go through an entire industrial transformation before it becomes something that can help a skyscraper stand. And that transformation is where this story actually gets interesting. So let's follow the mineral. First, extraction. Zircon doesn't get mined out of solid rock the way you'd picture a traditional quarry. Instead, heavy mineral sands operations dredge or excavate river and coastal deposits, where zircon has naturally concentrated alongside other dense minerals like rutile and ilmenite. This raw material comes from specific regions with the right geological history. Places in Australia, South Africa, and parts of Southeast Asia produce a huge share of the world's supply. And that source matters because not all sediment has commercially viable concentrations. Once the sand is pulled up, it heads to a wet concentration plant, where the real sorting begins. At this stage, the sand runs through spiral separators and gravity concentrators that exploit density differences. Zircon is significantly denser than ordinary quartz sand, so as the slurry moves through these systems, heavier mineral grains sink and separate from the lighter waste sand, which gets discarded or used elsewhere. This first pass can concentrate the valuable minerals from as little as 1 to 2% of the raw sand up to a mixture that's dramatically richer. But it's still not pure. That's why the material moves on to magnetic and electrostatic separation, where different minerals respond differently to magnetic fields and electrical charges, letting automated systems split zircon apart from ilmenite, rutile, and other byproducts with remarkable precision. Once isolated, the zircon concentrate is dried and often milled down into a fine powder, sometimes reaching purity levels above 99% for high-grade applications. That powder now enters the core transformation, and this is where the process shifts from simple separation to genuine chemical engineering. To make zircon useful in construction materials, particularly in advanced concretes, ceramics, and certain high-performance building components, it often gets processed into zirconium compounds through high-temperature treatment. In industrial furnaces, zircon sand can be heated past 1600 degrees Celsius, fusing it into zirconia, or breaking it down chemically to extract zirconium oxide, a compound prized for extraordinary heat resistance and structural stability. After that fusion stage, the material is cooled under carefully controlled temperature conditions, because cooling too fast or too slow changes the crystal structure and ruins the properties engineers are paying for. One wrong cooling curve, that is enough to ruin the batch. Once cooled, it's crushed, milled again, and calibrated into specific particle sizes depending on its final use, whether that's a refractory lining, a specialty ceramic component, or an additive that improves the durability of high-strength concrete used in super tall towers. And here's the thing you might not expect. Concrete alone, even reinforced with steel, has limits. It cracks under thermal stress, degrades under fire, and weakens over decades of exposure. Zirconium-based additives and refractory linings derived from zircon help address exactly those weaknesses, giving builders materials that resist heat, resist chemical erosion, and hold structural integrity in conditions that would break ordinary composites. By the time this material reaches the finishing stage, it's undergone extensive quality inspection. Processing plants run spectrographic analysis and grading protocols to confirm purity levels meet strict industry standards. Because a batch with too many impurities can compromise everything downstream, sometimes literally, in a 2,000-foot tower. Once graded and approved, the material is packaged, usually in sealed containers or bulk bags to prevent moisture contamination, and moved into a global supply chain that stretches from processing plants near river deltas to ports, then onto cargo ships, then to specialty manufacturers, who blend it into concrete formulations, ceramic tiles, or fireproofing materials used in major construction projects. The calibration happening in a facility near an Australian river directly determines how a building in Dubai or Shanghai performs under fire decades later. Now here's the complication nobody puts in the brochure. This supply chain is fragile. A huge share of the world's usable zircon comes from a small number of coastal and river-adjacent deposits, and those deposits aren't infinite. Mining operations are increasingly running into environmental pushback because dredging river systems and coastal dunes disrupts fragile ecosystems, displaces sediment patterns, and can damage habitats that took centuries to form. Ever wonder why some of these mining regions face fierce local opposition? This is why. Communities near these deposits often deal with landscape disruption and water table changes long after extraction ends. And then there's scale. The global zirconium and zircon market moves well over $1 billion annually, and demand keeps climbing as urban construction races skyward. Every super tall building under construction right now, and there are dozens in progress across Asia and the Middle East, is quietly dependent on mineral supply chains most people have never heard of. The tower gets the headlines. The mud, the dredge, the furnace, none of that gets mentioned. But without it, modern engineering ambitions stall. However, that dependency creates real vulnerability. If supply gets disrupted, whether through geopolitical tension, environmental regulation, or resource depletion, construction costs for high-performance materials can spike fast. And unlike steel or basic concrete, zircon-based materials don't have easy substitutes for every application, especially where extreme heat resistance is non-negotiable. So there's a trade-off baked into every skyscraper skyline. We get buildings that touch the clouds, engineered to withstand fire, pressure, and decades of stress. But the raw material enabling that comes from ecosystems getting quietly reshaped, river by river, dune by dune. So think back to where we started. A soft, unremarkable mineral pulled from river mud, sorted by density, purified through fire, and calibrated to fractions of a millimeter, ending up embedded in the tallest achievements of human engineering. It's a strange kind of poetry, honestly. The ground beneath a river becomes the backbone, hidden inside a building reaching toward the sky. And as cities keep building higher, that dependency isn't going away, it's deepening. Which raises a question worth sitting with. As we push architecture further into extremes, are we paying enough attention to what's being pulled out of the earth to get us there? If this kind of hidden industrial process fascinates you, the kind of thing that's shaping the world around you without ever getting noticed, make sure you're subscribed, because this channel exists to pull back that curtain every single week. Drop a comment and tell me what everyday object you want traced back to its raw material origin next. And if you learned something today, share this with someone who'd get a kick out of knowing skyscrapers secretly depend on river mud. Until next time, keep looking closer.